Welcome everybody to this seminar, this new stage on the seminar cycle. It's my pleasure to introduce Dr. Maya Garcia Coma to this seminar entitled Unusual November Elevated Stratosphere Event. Dr. Garcia Coma specializes in the study of the structure of the middle and upper Earth atmosphere. Started her scientific career here at the Institute in 2000. She is now Ramon y Cajal researcher at the atmospheres of the terrestrial planet group. And she defended her PhD thesis focused on the analysis of Earth atmospheres satellite data in 2004. So she stayed in an international stage in Germany, in the Max Planck Institute, for more than 2 years. And now she belongs to the science team of the space-based instrument MIPAS, SABER, and NOMAD. She's co-PI of the multispectral imager and Mesopause airglow MIMA instrument and their development here at the Institute. So Maya, it's your turn. Thank you.
Thank you very much, René, for the presentation. Well, today I'm going to talk to you about the Earth's atmosphere, and in particular, I'm going to focus on an event that we found in November 2009, which is an elevated stratopause. This event occurs because the stratopause goes up in altitude, very high up in the atmosphere. It goes up by about 30 kilometers. And it is generally related with sudden stratospheric warmings. So what I'm going to do is just to use this occasion to tell you a little bit more about the predecessors of these events, which are sudden stratospheric warmings. This is a very nice movie, which was taken from the news on TV last March, and actually they were talking about the sudden stratospheric warmings. Most of the media were using this information just to tell us about very cold weather that we were having in Northern Europe and also even in Spain. So maybe you have heard in March about this, and these events have become really popular among the public. And the reason why they are important for us, for the general public, is because they have effect in different regions in the atmosphere. In the surface, they affect the weather, and in the mid-atmosphere, it affects the ozone concentration, and in the upper atmosphere, it affects the density and indeed the satellite drag. But my intention in this talk is just to explain to you why these events are interesting by their own right, not just because the effects that affect us, the effects that have some effect on us, but because they are very interesting to study because they show really amazing circumstances of the Earth's atmosphere. So this is the outline of the talk. First, I'm going to give you an impression of the general conditions that we have in the polar winter in the Earth, and then I'll tell you about the sudden stratospheric warmings and also how they are related with, at some times, with elevated stratopause events. I'll tell you about their effects in the atmosphere, and you'll see how much they extend. And finally, I will tell you about the specific event that we found, and which is actually the main subject of the talk. I will try to explain what triggered this event. The atmosphere is a coupled system. Regions in the atmosphere are not individually behaving, but they are very well interconnected. So things that happen in some regions in the atmosphere, like let's say at some altitude or latitude, may propagate to other regions and affect the state there. And even further, these new states in these new regions may affect third regions, and so the whole system may change just with a very localized event. So this coupling comes from different parts. You have forcing from above, which comes from solar variability or for the injection of energetic particles in the pole. And also you have some forcing from below, which is generated by the internal waves in the atmosphere. So at the end, you have a full coupled system. And sudden stratospheric warmings are just extraordinary events that that are able to show the manifestation of this extremely interesting coupling. So in order to put you into context, I'd like to tell you what's the normal, the climatological situation that we have in the polar vortex. Here I'm showing mid-pass temperatures, and this is latitude here from the South Pole to the North Pole, and this is altitude from 10 to 100 kilometers. And in this particular plot, I position the summer in this left-hand side and the winter here. So this is the typical structure of temperature. You have in the lower stratosphere a cold region, and then you have a warm region around the stratopause, and then again colder in the mesopause. And the reason this warm region is formed here is because of the absorption of solar radiation by ozone, which even if it had its peak of maximum concentration around 20 or 30 kilometers, the peak of maximum heating is in this region here. However, during the night, there's no light to be absorbed by the ozone. But still, we have this warm region here. And the way this forms is because of the following. So here you have warmer temperatures and here colder temperatures just because there's no isolation. So you have a pressure gradient which goes poleward, a negative pressure gradient which goes poleward, and that way that induces an eastward circulation. So what you actually have is on top of the winter pole, you have a full cyclone turning all over the place. But this is not yet what produces this stratopause in the polar winter, because this way, if you have radiative equilibrium, you will have mainly temperatures decreasing with altitude. You have a new player, and these are the waves. Let me just introduce to you two types of waves by now. First, planetary waves. These are humongous waves that are formed in the surface, in the troposphere. They may have wavelengths of more than thousands of kilometers, and they are excited by generally warm and cold contrast by land and surface. And also they may be generated by the flow of very big mountain chains. So these waves happen to propagate just under eastward conditions, which are the ones that you have here in this region. They actually have, whether they are stationary or whether they are westward, so they only can propagate vertically under eastward winds. So that's what they do. They propagate outward, and then they break in this region here. Since they are westward, they exert some momentum deposition and accelerate the flow. When you have this acceleration of the flow, you induce a poleward circulation, which, as the wind converges in the pole, just goes downward. And when you have these downward displacements, then you actually have a compression of the atmosphere and therefore a warming due to adiabatic heating. So what you have is a warm region here, which is formed by this situation, and also this circulation that comes mainly, this is a cell mainly in the winter hemisphere. You also have a branch here, and this is what is called the Brewer-Dobson circulation. And the situation is kind of similar up here, because what travels out here are what are called gravity waves. These gravity waves are mesoscale waves. They are not that large, and they are generated also by in the top of the storms or just by the flow through small mountains. So again, these only westward propagating waves can go up in the atmosphere, and then they break. They do the same thing, and then you also have slight warming up in the mesosphere. But this situation is the general one, but sometimes can change, and can change dramatically by increasing temperatures in this stratopause level of more than 50K. And this is what the stratospheric warmings are. How do they occur? let me show you this plot because I'm going to show something similar along the talk. Here you have the Earth. Of course, the atmosphere is not that large. And here you have the troposphere up to 10 kilometers. Then the stratosphere, let's say, it depends on the latitude, but let's say around 55 kilometers. And then you have the mesopause, around 90, also depending on latitude. Then the thermosphere and the ionosphere may extend really high up, let's say 500 kilometers. So as I told you, you have this situation here. You have this cyclonic circulation on top of the pole. And then maybe, for some reason, you have these enhanced planetary waves. They may be created by different situations. And generally, these waves may produce an oscillation on the mean flow, but because they are transient, the waveguide is able to interact with the flow and just change the mean situation. So when they do that, they are able to revert the direction of this vortex. So instead of being cyclonic, they turn anticyclonic. In this situation, you have the opposite thing. They have been depositing this westward momentum now, this eastward momentum now, and then what you get is a strong descent here, but that adiabatically hits the region. Additionally, this downward situation enhances the circulation coming from the lower latitudes. So, and now something very interesting occurs. So you have this eastward flow in the bottom, then you have this westward or weakened situation above here. And then since the planetary waves cannot travel through this westward flow, they steadily start to break up at different altitudes. So what you see is that the stratopause, which has been heated extremely, just goes down with altitude. As I show here, it goes down. Finally, this full vortex may be reversed down to lower altitudes. And this is how they look like. If you take a time series of temperature as a function of altitude from 20 to 80 kilometers, these are results from MIPAS. You see, these are the anomalies, and here you see the normal situation, which you have a cold, warm, and cold region here. And you have a warming that goes down with altitude, and the level of breaking of planetary waves steadily goes down. And this is a really common event during the winter. Indeed, only 400% of the winters you don't find such an event. That means every 100 winters, you find quiet conditions in 4 of them. And because of that, they are frequent. They were discovered a long time ago, like in the 50s. They happen to be more frequent in the northern hemisphere, and this is logical in the sense that since planetary waves are generated by land-sea contrast, you have different orography in the southern hemisphere, so the planetary wave activity is significantly less. It is a process that begins in the troposphere and then has the biggest effect in the stratosphere, but it actually may extend to other parts of the globe and affecting chemistry, temperature, winds, and every atmospheric variable that you can imagine. So I'd like to tell you about the effects, general effects. This is a wonderful summary of the effects this is an EOS paper that summarizes very well the effect of the sudden stratospheric warming in which Bern participated. And I just kind of go through all of this. It would be too much. But I just try to pay attention in the ones that I think are going to be more interesting for you. And also the elevated stratopause itself, which is not here. So let's start what it does around the globe. For example, in the polar winter, where the stratospheric warming occurs, it affects directly the composition. And this is because when you weaken the vortex, you actually break the barrier with the rest of the latitudes. And that means that air may enter, and then mix with the otherwise very isolated vortex. This is the case of ozone, for example. This is just one example. Now, this comes from a sudden stratospheric warming in the southern hemisphere. It was the only one observed up to date in the southern hemisphere. And I just put it here to show you this particular situation. So when you have no stratospheric warming, you have this distribution of ozone, where you have less concentration over Antarctica. However, when you have the stratospheric warming, you see how the air may enter and then mix with the air on top of the polar winter and actually increase the mean concentration of ozone. This is what I show here. You see latitude here. This is the southern pole now. And this is altitude from 10 to 50 kilometers. So you see a clear enhancement here of ozone over the pole. As I said at the very beginning, it also affects the tropospheric weather. And the way it does this is not very well understood. It might be related with reflection of planetary waves, but it's not very clear how it propagates downward to the surface, since the reversal just reaches the stratospheric altitudes. So what happens is that because you have a change situation over the pole, the gradient of pressures are changed. So you have a relatively higher pressure level at high latitudes with respect to the low latitudes. And this is something which is opposite to what we call the non-positive phase. It is the normal weather where you have the polar jet stream here, which has small meanders here. And so the vortex is kind of isolated. So when these stratospheric disturbances just go down to the troposphere, they are able to change the northern hand mode in the way that the jet gets really distorted. This way, the cold part of the cold air from the pole just goes really into low regions. And this also creates blocking systems that change the track of the storms. So that way you have, in the north of Europe, you may have regions of very cold weather, as in North America, and also you may have a lot of rain around the Mediterranean. But there's also a response higher up in the atmosphere. In the region above, the mesosphere and the thermosphere, the effect of stratospheric warming is also very nicely seen. Remember the situation. We have a reversed vortex or a weakened vortex. You have this westward flow. And then in this westward flow, what can travel up there are just gravity waves which have eastward propagation. And that way they deposit eastward momentum, affecting also the zonal mean there, and even reversing it at some time. At that time, then this produces adiabatic cooling, just because the air goes into the atmosphere and then goes up here and just reverses the situation up here. So you have a cooling in this region, and you can see it here. I showed before, this was the stratospheric warming in the stratosphere, and this, you can see how the region cooled right above. But again, because of this circulation, this sucks the air from above. Now you have downwelling here, and again, downwelling, you have a compression and then a warming. So again, the warming here, and this goes up, and you have a cooling up there. So this really goes up in the atmosphere, extending to very high altitudes. But very interestingly, these stratospheric warmings have effect in all the places which are not the pole. This is one example I'm going to show about. We have some others. For example, you have also an effect in the summer pole when you have changes in polar mesospheric clouds that are formed there. But anyway, regarding this process here, you have an effect on ozone in the equatorial stratosphere. imagine again this enhanced Brewer-Dobson circulation here, this enhanced circulation here, which actually takes air from lower regions up in the atmosphere. That brings ozone, which has maximum concentrations here, up to higher altitudes. That, together with the cooling because of the ascending air, makes that ozone is very abundant here. So you can see it here. You have latitude here, and this is the time series. And around the equator, you have a clear enhancement in ozone in these regions. And very, very nicely, because ozone is the responsible of excitation of the tides around the equator when absorbing daytime radiation, the tides are changed. And these tides have can propagate really high in the atmosphere. They go so high that may affect distributions in the atmosphere. So they have effects on the electric field and therefore on plasma motions, but also on winds. And when you have effect in winds, you may move air parcels up and down, where you go to regions where maybe electron recombination is more effective. So finally, the electron density changes. And also, this changes the density in these regions high up there. And this is what really high altitudes, like let's say 400 kilometers. And this is where it actually affects satellite drag. So there are several other things that may happen, but really don't have time to go through them. So I'm just going to go on with what's the next step in the evolution of the stratospheric warming. So sometimes during the recovery phase, something very special happens. You have the strat warming, these westward and eastward on top circulations, and then the warming in this region here ends just basically through a radiative relaxation. So you finally end up with a near isothermal vertical structure. You have gone with this westward, or at least a weakened flow down in the atmosphere. Planetary waves cannot propagate upward anymore, so you have a very low planetary wave activity now, and a near isothermal region. In this near isothermal region, what you have is a more stable situation. In that way, gravity waves can travel really high up in the atmosphere without being broken. And then the vortex recovers around 60 kilometers, just because you have, again, a really slightly colder region here. So it starts recovering there. Under this situation, the gravity waves with westward direction propagate high up in the atmosphere and exert a strong westward forcing. And then really high up in the atmosphere, they produce a very strong downwelling, which again produces this warming. And as in the case of the formation of the stratospheric warming, the changing level of the region where the waves break just go down, and then you see this warming and downwelling just going lower in the atmosphere. And this is what an elevated stratopause is. And this is how it looks like. So you have the warming here, and then, as you remember, the stratopause went down in the atmosphere, and then it suddenly jumps, in this example, from 30 to 80 kilometers. And then it goes down with altitude as time goes by. And how often is a NEAS form, an elevated stratopause form? Well, it usually has been connected with major sudden stratospheric warmings. Major warmings are the ones that not only weaken the region, but just reverse the vortex. However, the models are able to predict the formation of these events under, let's say, nicer situation in which the vortex is weakened and the stratospheric warming is not that high. But this has not been observed very often. Indeed, it has been observed only once in 2012, and that was in midwinter. That was in January. As you can see here, just because you have the largest contrast with land and sea temperatures, the extent of the activity of the planetary waves is larger during January, and that makes the sudden stratospheric warmings are really more frequent around January. So in the case of November, you have only like 8%, from 4 to 8% probability of having a sudden stratospheric warming, and out of that, only 2% should be accompanied by an elevated stratopause. So really the possibility of finding such an event in November is only 2 out of 100 Novembers. But we were so lucky, and we found it. We found it in MIPA's data. This is temperature without the ES. This is how it looks normally. Remember the stratopause here, the cold region here, and the cold region here. And this is what we found. In November 2009, we found extreme heating, warming of the mesopause, of the upper mesosphere, which went up to 260 K, which is similar to what is found in really strong stratospheric warmings. Let me show you the structure, the vertical structure. Here I'm showing the December mean. These are slices, cross-section, just if you look at the pole from the top and you go up in altitude. So the pole is here, the North Pole is here. And you see that there's the cold region here, and then the warm region in the stratopause, and then again it cools as you go up in the atmosphere. This is the climatological state. But in the event that we found, we have a similar situation, low down in the stratosphere, but there's like a kind of hole of cold air here, which finally warms really strongly, around 82 kilometers. And let's focus on this altitude here, around 60. If we don't look at temperature, but at some other variables, in this case, I looked at carbon monoxide and altitude. When you have no elevated stratopause and when you have elevated stratopause, you see a clear difference. During this elevated stratopause, this very strong downwelling that I was telling you about is able to make species intrusions that are very abundant in the mesosphere down to the stratosphere. So this is the case when you don't have in the ES, almost no carbon monoxide. However, around this region where the ES occurred, you have levels of CO which go up to 3 parts per million, which is quite a lot. It's like 200% more than what you expect. And also, if you look at the altitude, the change in altitude in this pressure level, I mean, if you were looking at a pressure level and you'd see how the geopotential height was changing in this level, you see that the normal downwelling in the winter produces altitudes in this level of around, let's say, 50 or 49. But in the case of the ES, we could go out, this is wrong, we could go down to some 48 kilometers, which is quite significant. And this is the evolution inside the vortex. This is something similar to what I showed you before. This is time here. Again, this is altitude, and this is temperature, and this is carbon monoxide. Well, you see these gray regions here. This is because MIPAS is not able to measure above 70 kilometers all the time, just at certain dates when you have these special modes of observation. But we were so lucky that precisely the day that this was happening, we were measuring, and then we had some other days where to compare with where the ES was not happening. So as you see here, you have this warming in this region, but the down progression of the stratopause is not present here. It's just because, I mean, it was really, really, really weak. I'll show you later that it actually existed. So again, you have this situation with the warming, and then this very favorable isothermal atmosphere with, where gravity waves finally are able to propagate very very well up to high atmosphere, up to the high atmosphere, and then you have the warming that went down with altitude. Finally, in this region, you come to the climatological state. And in the case of carbon monoxide, you see how at the beginning, there's no intrusion in the stratosphere. However, as time progresses and this downwelling goes to reaches really low altitudes, you see how the intrusion of carbon monoxide looks like. And this means that you have mesospheric carbon monoxide that went down about 15 kilometers into the atmosphere. There are some other species, well, actually all of them are affected by that. But let me talk to you about water vapor. First of all, because I'm a fan of mesospheric water vapor, and secondly, because it has really, it shows very well the downwelling, and it also has effects in some other species. Here you have a similar time series as a function of altitude, and because you have less concentration of water vapor up there, just because this is brought to the winter pole by the Brewer-Dobson circulation. When you have this downwelling, what you're doing is you're injecting this very dry air into the atmosphere. Because you have really dry air, then you have less concentration of atomic hydrogen. And atomic hydrogen is one of the responsibles for the destruction of ozone in these altitudes. So what you find is that at the same time that you have these elevated stratopause, you have a significant increase in ozone. Another species that are affected are the nitrogen oxides, which are represented here, NO plus NO2. And then you can see how these are injected in the lower stratosphere. This is very important because this region here, the reason why you might have high concentration of nitrogen oxides there is because of the electric particle precipitation that plays an important role during the polar winter. The downwelling of these compounds may have an impact they increase the stratospheric amounts by 40%. This finally has effects on the ozone concentration. So it is very interesting to know how the winter progresses and how these species are injected down there. We compared all these results with model predictions. I'm not going to show that here. I'm just going to show you an example. We compare with WOCAM. WOCAM is a high-top model that is, let's say, plugged with the atmospheric behavior at lower latitudes, at lower altitudes, and that way it can represent the atmosphere very well with time in higher regions. So if you compare the NOx in our MIPAS measurements with WOCAM measurements, you see that this downwelling was very well represented. So we are pretty confident that these observations are real. And what triggered this ES, this elevated stratopause event? So these are a lot of plots of temperature, cross sections. This is pressure. This is it doesn't matter that you don't see it. This is the stratosphere, and this goes from 60 north to 90 north. So we are really centered on top of the winter pole. And this is the middle of the month. This is the end of the month. Just remember that the ES occurred here. So at the beginning, there was this, actually the strat worm was started here, but I had no room for more plots. And so initially you have the normal conditions in which you have a cold region here, but as the weekend vortex went down, it affected temperatures, and at some point you really had a warming, but very well confined to very high latitudes. Here, it seemed to recover. It seemed to disappear. But again, you had a new boost here. And again, you had another small stratospheric warming here. And then this started to cool relatively until you came to this situation in which you had the ES. And if one looks to the zonal winds. These were taken not for MIPAS, but from MERA reanalysis. These are models that take information from measurements, but actually simulate what you have in the atmosphere. So if you look at the zonal mean zonal winds, these are similar plots evolving with time from mid-November to the end of November. And you see that at the beginning you had the normal vortex eastward, which is shown in green, the eastward, and then you start to see this westward, or this weakening in this region here. And then it appeared, really went down in altitude. But then it disappeared, as I said before. But eventually, this reversal appeared strongly low in the atmosphere. At this time that you have really strong westward winds, but very confined to high latitudes, then you did not have this planetary wave progression in altitude. And that was what led this isothermal profile, vertical profile, to let the gravity waves to hit the atmosphere in the higher altitudes. And what triggered this stratospheric warming? Well, the stratospheric warming was triggered by, as usual, planetary waves. And this is the time series of planetary waves as a function this time of latitude. You have the North Pole here, and this is 30 north. Planetary waves usually are confined to 50, 80 north. So you see as time goes by, around 18th of November, you had the first boost, and then a second pulse, strong one, around the 22nd. Then you had this time when you had decreased planetary wave activity, and finally, at that time here, that you had the ES. And just the last picture I'm going to show is how the situation was when you were looking at the potential vorticity at that point. Potential vorticity is a very interesting quantity because it can show you how the winds turn, and indeed you have movement of air parcels through the lines of same color because these show the track of adiabatic motion. So in the lower panel, I'm showing 10 millibar level, which is in the mid-stratosphere, around 30 kilometers down here. And at the same time, you will see what happens high up in the atmosphere. This is the movie that didn't work, so I'm going to go to the GIF and try to be fast because I cannot stop it. So let's look at the lower panel first. You see the normal vortex here, kind of displaced already around the 10th of November. So then you see how it's displaced here, but then how this anticyclone forms here, and another one here. This really weakens the vortex here. And several days later, because of the propagation of the waves, what you have is a really strong formation of the vortex there, which was the responsible for this strong downwelling high in the atmosphere, and that resulted in this ES formation. So these are the conclusions. I showed that MIPAS measured this, from my point of view, a spectacular elevated stratopause event in November 2009, which was comparable to situations where you had a really strong southern stratospheric warmings. Because it was in November, we think is very interesting because these are really rare events. And in the case of minor warmings, they should be found only 100% of the times. The characteristics of the event itself is that it was really highly asymmetric and had this very strong downwelling, which was very unuseful for this time of the year. We found something that you generally find with these events, which is increased stratospheric composition of otherwise mesospheric species. NOx, you have it down there also, but injection of these species, and then an affection of the ozone tertiary maximum at lower altitudes. So we saw in the movie that the disruption was produced by the formation of these two anticyclones, and indeed this has very high similarities with the starting of what we call Canadian warmings, which are really soft warmings, but that have effect over Canada. And as these kind of events, we didn't see a major warming, a full vortex reversal, but only a weakening of the vortex. So we think that this detection suggests that ES may occur in combination with really weaker events that we were not taking into account before. Indeed, when you do studies of the polar winter, you normally don't go back to November, back to the end of autumn. So because these events seem to happen earlier than previously thought, we think it is important just to take into account these times into the year just to understand the polar winter variability. And just coming to the first question or the second question I made, why are these sudden stratospheric warmings important? I hope that I showed you that not only because they affect us, but because by their own right. And by their own right, because the way they affect different regions in the atmosphere is really spectacular, in the sense that they couple different regions, and if we study them, we will be able to make a better forecast of the situation, of the state of the atmosphere, and to understand the behavior when you have extreme events. And also because this shows the coupling of different regions. It is interesting to study them just to know the relative roles of the different processes taking part. And because of our discovery, we would like to point that the range of polar variability, polar winter variability, is important to be taken into account earlier in the autumn, because this may affect chemistry and eventually the trends. So that's all.
So now the seminar is open for questions. Please wait the micro so the question can be recorded and reported to the person that is listening to questions.
To the Arctic?
With the
altitude.
Yes. Do you expect to have it at 80 kilometers, 95, 75, or does it change?
Well, you usually might have a change in the altitude just because of the regime of the vortex, because the propagation of the waves just depends on the structure of the vortex. But in this particular case, it went really up. It was, as I said, it was they usually go up to this altitude at the most, and this event reached that altitude as well. But the altitude may change from 70 to 80 depending on the event.
My question's probably, and it may be stupid because I'm completely ignorant. So, is there any way of forecasting those events?
In particularly the elevated stratopause, yes. You might be able to, if you actually include in your models the exact situation in the lower part of the atmosphere, you may eventually, with, I don't know, maybe 5 days in advance, you might be able to forecast them. The problem is that the models generally underestimate these events. In particularly, WOCAM was not able to reproduce it. And the reason because of that is they might be underestimating the gravity wave drag in the upper atmosphere. So once that you are able to understand very well the mechanisms, and you are able to parameterize these waves well in the models, then of course you would be able to have a good forecast previous days in advance.
have you seen any other events? Would you expect if we said at the end in the conclusions that maybe minor disturbances could introduce elevated stratosphere, would you expect that to happen in the southern hemisphere?
In the southern hemisphere? Well, you have to have this isothermal profile at the end. And then you have to have a strong change in the planetary wave activity. That would be a crack. I mean, just to find this event in the southern hemisphere. But eventually, there's not a particular reason why you shouldn't have it. But I think that would be really, really not very much probable. And regarding what you mentioned about data, well, we do have a lot of data in this region here. In the case of MIPAS, it's true that it happens every 5 days that we have measurements up there. But these measurements are extended in time for a long time. So we really have a lot of information of the region. And another instrument that is looking at, there are several instruments. You have MLS, you have ACE, but another instrument that we work with is SABRE. And this instrument also gives a lot of information. However, at that time of the year, it was actually looking at the other hemisphere, and that's why we don't have data for that. But we do have a lot of data for the mesosphere in the Earth. Well, I actually think that not exactly this strong, but will be happening during the polar winter, which have not been looked into much.
Okay, I think it's all. Thank you, Maya, again.